So I'm not going to do all the problems in this, all the even problems. It just takes too much time. And I think at some point they're not particularly hard. The newness, the only variation in the problems that we get in this section is some of the problems aren't factored, which makes it easier for some of the parts but harder for the x-intercepts. If in problem 10 I wanted to do part A, least each x-intercept and its multiplicity, for 10A, which will be similar to your 9A, you have to take the function and set it equal to 0. Well, if the function's not factored, you need to get it factored. So the first step in finding my intercepts when a x-intercept, if the problem's not factored, is to get it factored. And this is just easy factoring. The parentheses are going to lead with a couple of x's, and then my parentheses at the end, the numbers are going to need to multiply to -7 and add to -6. It's really subtracting because they're going to have opposite signs. And the numbers for my parentheses are going to be 1 and -7, because if you multiply 1 and -7, you get -7. If you add 1 and -7, because they have opposite signs, you really subtract and you'll get that -6. So the factoring, hopefully you can do that without me explaining the factoring. Once I get it factored, the factor of x plus 1 is going to give the x-coordinate of the x-intercept of -1. The x-intercept from that factor is going to be -1, 0. And it's going to have multiplicity of 1 because the exponent is an implied 1 outside that parentheses, which is odd. The factor of x minus 7 is going to give an x-coordinate of my x-intercept of 7. The x-intercept is going to be 7, 0. And this is going to have the same multiplicity of 1, which is odd. So that's everything for part A. For part B, because both factors, both x-intercepts have odd multiplicity or multiplicity of 1, for 10B, the graph will cross the x-axis at both x-intercepts. The nice thing about this problem is the C and E is easy. When it's multiplied out, to get the maximum number of turning points, I just take the highest exponent and subtract 1. The maximum number of turning points is 1. And when it's multiplied out, the graph is going to resemble the leading term, which is x squared. To sketch a graph, I'm going to enter this. This is just a baby parabola. I doubt that I need to go to the 200s, but I will, and I'll just progressively go in smaller. So I'm going to enter the function x squared minus 6x minus 7. Always leave my x's at the 10s. That will work for 90% of the problems we do. If I made my y's like the 200s, boy, that vertex is nowhere close to the bottom of my screen, so let me recalibrate, maybe go down to the 100s. And this is just a matter of getting a picture that I'm happy with. It's getting better. I think I could even go further because this vertex is so far from the bottom. Let me go to the 50s and just try to get my minimum point, to be closer to the bottom of the screen than the middle of the screen. Yeah, maybe that's good enough. I probably could even go down further. Maybe I could go down to the 25s. And this is not scientific at all. This is just a matter of getting something that I don't mind the way it looks, meaning the maximum and minimum points are the minimum points towards the bottom of the screen, the maximum point towards the top of the screen. This seems reasonable. Now I'm going to I know what the intercepts are. I just need to find that point. I find that point by hitting my calc trace key. It's a minimum point, so I go down to option 3, get my cursor using the left or right arrow, so it's a little bit to the left of the minimum point, and then hit enter, and then get my cursor a little bit to the right of the minimum point, and hit enter, and then get my cursor as close as I can to the minimum point, and hit enter. And this is a nice one. That's going to round to 3. My calculator doesn't do algebra. It doesn't know that the vertex is 3, negative 16. But I'm going to round that 2.99 to 3 and have my graph show the vertex of 3, negative 16, the x-intercept where the graph crosses the x-axis of negative 1, 0, the x-intercept of positive 7, 0 where the graph crosses the x-axis. So that's the end of part D. I've sketched a graph, approximated my turning points. Now for increasing and decreasing, I'm just going to make the left half and the right half. The left half goes from negative infinity to the x-coordinate of the vertex, which is 3. The right half goes from the x-coordinate of the vertex, which is 3, to infinity. For part F, this is the increasing interval. The graph is going up on that side. So this graph is increasing from 3 to infinity. This is the decreasing interval because the graph is getting lower as I move from left to right on the left-hand side of the graph. And that's everything for 10. Your problem 9 should work exactly the same way. It even has the same vertex It even has the same vertex. The x-intercepts are flip-flopped. I flip-flopped the signs because I flip-flopped the sign. The only thing that's going to be different is when you factor it, your signs are going to be flipped, and you'll get, a similar problem. So one more graphing, and then we'll get to the last new concept, which isn't particularly hard either. So I'm going to work on number 14 while you get to work on number 13. And it's not factored. So in order to find the x-intercept, I set it equal to 0. I factor it. It's a little bit harder factoring because there's a common factor that I need to factor out to do this properly. So to get started with 14a, because it isn't factored, I have to do the factoring to find the x-intercepts. Each term has an x, so I can factor out an x. The first term is negative, I need to factor out a negative, and all the numbers are divisible by 3, I need to factor out a 3. The first step in my factoring is to factor out a common factor of negative 3x. After I factor out that common factor, when you factor out a negative, you need to flip the signs. That positive sign is going to flip to negative, that positive sign is going to flip to negative, that negative sign is going to flip to positive. In addition to flipping the signs, I need to divide the numbers by 3 and take an x away. When I divide that 3 by 3, I get a 1. When I take an x away from the x cubed, I'm left with an x squared. When I divide that by 3, I get a 1. When I take an x away from the x squared, I'm left with an x. When I divide that 18 by 3, I get a 6. And when I take the x away, I'm just left with the 6. That's partially factored. Now I need to completely factor this. I'm going to emphasize this first factor has an exponent of 1. I'm going to factor this without explaining. This factors into x plus 2 times x minus 3 because the numbers I put at the end of my parentheses need to multiply to negative 6 and subtract to negative 1. And now, each of the factors has an exponent of 1, has multiplicity of 1, which is odd multiplicity. The factor of negative 3x, when you set it equal to 0, you would divide both sides by negative 3 and get x equal to 0. That's the x-coordinate of the x-intercept. So the x-intercept from that is going to be 0, 0. It has multiplicity of 1, which is odd. This middle factor would give an x-intercept of negative 2, 0, which also has multiplicity of 1, which is odd. And this far right factor would give an x-intercept of 3, 0, and that has multiplicity of 1, which is odd. When we have odd multiplicity, the graph crosses. So for part B, because it crosses on each one, I'm not going to separate and say it does this for that and that for this. I'll maybe just say it crosses at each. Rather than saying it crosses at 0, 0, it crosses at negative 2, 0, and crosses at 3, 0. So that was part A. Part B, the maximum number of turning points when you need to do the factoring is just the highest exponent minus 1. The maximum number of turning points is 3 minus 1, which is 2. And when it's all multiplied out and it's not factored, the end behavior is just the leading term, which is the negative 3x cubed. Now I need to sketch a graph, find the maximum point and the minimum point, round them to 2 decimals. Real quickly, just to get you practiced on that. Y equals clear negative 3x cubed plus 3x squared plus 18x. Window, let me just go out to the 200s. Hit my graph. If the max and mins are close to the top and the bottom, I'm good. They're way away. Look how far the max and the min are away. I'm going to scrunch it way down. I'm going to go all the way down to the 50s on the y's to try to get those maximums and minimums closer to the bottom and the top of the screen. Yeah, I could probably even go a little bit further down. Maybe I can go down to the 40s. It doesn't matter. There isn't a right window. It's just, I like having my maximum and my minimums close to the bottom and the top of the screen, and I like symmetry. That's got to be good enough. Let me find my minimum point, round to 2 decimals, do second, trace, go down to option 3, get my cursor flashing to a little to the left of the minimum point, hit enter, and then trace back around to the other side, get my cursor flashing to a little to the right of the minimum point, hit enter, and then get as close as I can to the minimum point, hit enter, and I'm going to say 1.12, negative 12.18. It's actually negative 1.12, negative 12.18, so negative 1.12, negative 12.8 is one of the points that I'm going to need to plot on top of the intercepts, and I need this maximum point. I do second calc, go down to maximum, use my cursor to get my blinking cursor a little bit to the right of the maximum point, hit enter, then I go around to the opposite side, get my cursor flashing a little to the right of the maximum point, hit enter, and then I get as close as I can to the maximum point, hit enter, and I'm going to say that's 1.79, 24.63 rounded to 2 decimal places. So I didn't even round right there. That probably should be 1.79, but I won't take off if you round. I mean, that's hardly that big of a deal. So, and then just plot those points, plot the maximum point, plot the minimum point, plot the 3 x-intercepts, and draw that, whatever you want to call that shape, between them. And now I'm going to do the increasing and decreasing, set the function up into intervals. First interval goes from the far left edge of the x-axis, which is negative infinity, to negative 1.12. Middle interval goes from negative 1.12 to what I should have written as 1.79. And the far right interval goes from 1.79 to infinity. This goes decreasing, increasing, decreasing. So that's a decreasing interval. This is an increasing interval, and that's a decreasing interval. So for an answer to part F, it's increasing in the interval negative 1.12 to 1.79. It's decreasing in the interval negative infinity to negative 1.12, and then again in the interval 1.79 to infinity, put a union between. So one new concept, it's an easy concept, and it's a lot like something we did in the last chapter. So I'm supposed to create a polynomial that passes through the points, or that has those as the x-intercepts, that also goes through another point. I'm going to create a function that has x-intercepts of positive 3 and negative 3. For a function to have an x-intercept of positive 3, it has to have a factor of x minus 3, because I'd set that equal to 0 to get the 3, 0. For a polynomial to have an x-intercept of negative 4, 0, it would have to have a factor of x plus 4, because I'd set that equal to 0, that would give me negative 4, I'd create that x-intercept. So this graph, if I graph the function f of x equals that, it's going to have x-intercepts of 3, 0 and negative 4, 0. I have no idea if it will pass through the point 2, negative 12. So what I need to do is force my graph to pass through the point 2, negative 12. How do I do that? I do that by sneaking a number to the left of the factoring or the left of the factors that give my intercepts, and I do algebra to figure out what number I can put in front of those parentheses so that the graph is going to go through this. Apparently, the number is going to be 2 because I graphed the function 2 times x minus 3 times x plus 4, and it had an x-intercept of 3, 0. It had an x-intercept of negative 4, 0, and it passed through the point 2, negative 12. How do I make this a into 2 what it needs to be? Super easy. I take the negative 12, that's the y-coordinate of the point that it needs to pass through, change the left-hand side of my equation to that, change both x's in my factorings to the x-coordinate of the point that it needs to pass through, and then just do the math. This gives me negative 12 equals a times negative 1 times 6. That gives me negative 12 equals negative 6a. Divide by negative 6, divide by negative 6. I get 2 equal to a. I change this a to 2, and that polynomial will have x-intercepts of 3, 0, negative 4, 0, and in addition it will go through the point 2, negative 12. Well, that was your 17. Stole it from you. Oh well, is what it is. I should have done 18. Your 19 should work remarkably similarly. I'm going to go ahead and do 20. On 20, I want the x-intercepts to be 2, 0, and 4, 0. To get an x-intercept of 2, 0, I would need a factor of x minus 2. To get an x-intercept of negative 4, 0, I would need a factor of x plus 4. Those, if you set them equal to 0, you'd get 2 and negative 4, which are the intercepts that you need. So this function by itself is automatically going to have the right x-intercepts. I need it to go through the point 3, negative 21. To do that, I put a negative 21 to the left of an equal sign, and inside each parentheses, I change the x's to 3. That's going to give me negative 21 equals to 7a, and then just divide by 7, divide by 7. I get negative 3 equals to a. I take that negative 3 and put it before the parentheses. That function, when you graph it, it has the right x-intercepts. It has an x-intercept of negative 4, 0 and positive 2, 0, and it passes through the point 3, negative 21. One more problem, and we'll call it the end of this section. Your problem 21 is more or less the twin of my problem 22. I'd like to make my odds and evens work the same. So I need exponent of x-intercept of negative 2, 0, but multiplicity 2, and an x-intercept of 4, 0. It's an implied multiplicity of 1 if I don't say the multiplicity. So my function needs to have an x-intercept of negative 2, which would have a factor of x plus 2, multiplicity of 2, so I get an exponent of 2. X-intercept of 4, 0 gives me a factor of x minus 4. I'm assuming the multiplicity is 1. And I need to force it to pass through the point 3, negative 100. I do that by taking the y-coordinate of the point, putting it to the left of the equal sign, taking the x-coordinate of the point and plugging it in both parentheses. This is going to give me negative 100 equals a, and then the first parentheses will be a 5. I have to square it. Second parentheses is going to be a negative 1. This gives me negative 100 equals a times 25 times negative 1. This gives me negative 100 equals negative 25a. Divide both sides by negative 25. That's going to give me positive 4 equal to a. So in my answer, I'll put a 4 behind the parentheses that has an x minus 4 and an x plus 2 squared. Plus I flip-flop the order here. It doesn't matter. I just, for whatever reason, I put the x plus 2 squared second. Wouldn't matter at all if I wrote my answer is 4 times x plus 2 to the second times x minus 4. Because multiplication is commutative, the order that you write the factors in is not such a big deal. So you should be able to do problem 21. And there's actually one more, problem 23. You should be able to do that as well. There's nothing new in those style of problems. All right, so that was monstrously long. There are really unbalanced sections. There's a couple long sections, a couple short sections. We only have 5 sections in this chapter.